Let's take a look at the setup of this problem. Okay, there's a small plastic sphere, and it's at some distance from a second small plastic sphere. And the first sphere has a charge of -5 nanocoulombs, or -5 times 10 to the minus ninth coulombs. The second sphere, okay, which is at some distance, has a charge of -12 nanocoulombs, or -12 times 10 to the minus ninth coulombs. So we have these two charged spheres. Now we know two charged spheres, both negatively charged, will exert a repulsive force. Okay, we know that's true. And we're told that the two spheres repel each other, and we're given the magnitude of the repulsive force. It's 8.2 times 10 to the minus fourth newtons. And of course, these forces will be equal and opposite. And what we're asked to find is this. We're asked to find the distance between the two spheres. That's not given to us. We're asked to find this distance. So here's a setup, and we start with a picture, as we so often do. This is a straightforward Coulomb's law problem. We know if I have two negatively charged spheres, the forces between them will be equal and opposite. They'll repel each other. Okay, we know that's true. We can also calculate the magnitude of the repulsive force. It's equal to the electrostatic constant K times the magnitude of charge Q1 times the magnitude of the charge Q2 divided by the square of the distance between them. Well, in this case, we know the force, we don't know the distance, so we can rewrite the equation. So we can solve for the distance in terms of the force. So we just rewrite this equation. And the distance is the square root of K times the magnitude of Q1 times the magnitude of Q2 divided by the force. So we've just rewritten the Coulomb's law equation so that it looks like this. We know the numbers for Q1, for Q2, and for the force. We're just going to solve for the distance. And before we do that, before we complete our solution, let's do an assessment. What do we expect the answer to look like? Well, for charges on the order of a few nanocoulombs, for forces on the order of a millinewton or so, we've seen distances that are on the order of a few centimeters. Okay, so for nanocoulomb charges, millinewton forces, distances of a few centimeters is what we expect. And we're going to do that assessment before we complete our calculation. And so when we finish our result, if we get something that matches this, that will give us confidence. Our solution is pretty straightforward. All we do is we take the numbers that we're given and put them into this relationship. So it's the square root of the electrostatic constant, that's 9 times 10 to the ninth, times the magnitude of charge Q1, that's 5 times 10 to the minus ninth, times the magnitude of charge Q2, that's 12 times 10 to the minus ninth, divided by the force, and the magnitude of the force is 8.2 times 10 to the minus fourth newtons. We take a square root of everything inside this expression, and what we get is a distance of 0.026 meters, or rewriting that in centimeters, 2.6 centimeters. That's what we calculate for the distance between the two spheres, and our assessment is this. We predicted before we calculated that the distance should be a few centimeters. That's exactly what we find, and so this calculation matches the way we know the world works.